I'm here. Let's get started. Good afternoon, everybody. Welcome to another exciting afternoon of organic chemistry with your host, me, Dr. White. All right, important things. A week from today will be test one. Test one will cover hydrocarbons, alkanes, cycloalkanes, also alkenes, alkynes, and aromatics. I think that's chapters 2, 3, and 4 I have. Listen carefully. Next couple days, by Monday at the latest, hopefully over the weekend, I will put a post on Blackboard School on D2L and also send out an email with one, just what I just said, what's covered on test number one. The other thing, how many pages, how many problems, and it's 100 points, uh, 10 times 10. And I think all that vital information. I'll talk more next week how we're going to do test number one, but essentially I'll be sending it out as a PDF file that's word protected. You'll download it, and we won't do it during our class time. I'll let you do it afterward. And the next day you'll upload it as a single PDF file or a Word document, whichever you like. And I have a file I'll be sending, or it's on Black D2L already. If you don't have a scanner, but I assume everybody has a cell phone, that you can take pictures of it and then make it into a PDF file. Summer worked great for my class that I taught at another school, 9-page test. Now, if you don't have a printer, you can just write out your answers. You don't have to rewrite the whole test, and then take a picture of it if you don't have a scanner. And like I said, it worked out beautifully. A lot of work for me because unlike paper, I got to open up, but by having it in PDF files or Word file, it works good. All right, that's the one thing I wanted to talk about. And next, later today, we'll be doing lab number 2. I didn't do it, but I'll send out an email. Make sure today, or I'll give you till tomorrow, you have the first lab uploaded in the assignment areas of D2L, so you get full credit. Also, I haven't pushed it yet, and I'll be sending out emails because should for an online course like this. Don't forget to do your problem set 1, just do some of them and upload it so you get your 1 point for that problem set. And I'll send out an email on that. One of the good news is since the 3rd of September, I've been taking this online course on how to teach online courses, which all faculty who haven't taught online courses at ECC had to take, either now or during the summer. And I didn't get in the class filled up in the summer too quick, so I had to take it now. And it's been sucking up a lot of my time, really a lot. I'll be done today, and then I'll have more time with you people, which means I'll be sending out more announcements to remind you what to do, because unlike a face-to-face in a classroom, you may not hear my announcements. If you're not here or you miss it, log in late, whatever. All right, any questions so far? Remember, in my class, there's no such thing as a dumb question. All right, let's talk about the problem set on alkenes, alkynes. Let me just remind you, on Monday, I will be doing the aromatic problem set, which I highly recommend you do before I do them, so you can ask questions. And I'll be doing my world famous review for the next test. Now, one thing I noticed with a student Monday night, and don't forget tonight I have my office hours if you need help, 6 to 7:15. If you need me to stay later, I do, because I don't have to rush home because I'm already home. But anyways, D2L is sort of old and funky. And if you scroll down like on the lectures, you'll see a little button there that says more or see more. And it doesn't show everything in that folder, which is pretty stupid, but that's D2L. It's old and funky. And that's one of the ways it's funky, or actually awful. So just a reminder. All right. Any questions? All right, let's get to work. I promise I go through the alkanes, alkenes, alkynes problem set. Like I did for the first one, I'll do one page at a time. If you'd like me to do one, let me know. I'll do it, go through it. Once in a while in problem sets, I have a wrong answer. I've been too lazy to correct it. One of these days I will. So let's get to work. Wrong one. All right, thumbs up, people. Can you see the alkenes problem set? Thank you. Some of you have the world's fastest thumbs up. Thank you. All right, let's go through it. On test number one, and throughout the semester, but especially test number one, you should know two skills for nomenclature problems. The first one is give the IUPAC name for the following. And you should know when you look at a compound, first thing, look for what's different. What's not a carbon-carbon seal? Oh, a double bond in a ring, 6-membered ring, cyclohexane, but for double bonds, drop the A and E at the end of cyclohexane and replace it with ENE. When it's in a ring, one double bonds has to be one, the other two. This is a pretty sophisticated question. This one's a little on the hard side. And you don't put that number. Because of that, to give the lowest numbers on the alkyl groups, the methyl and ethyl, it has to be 1-methyl, 3-ethyl. Because if I made this one 1, then the methyl would be on 2, 3, 4, 5, 6 on the ethyl. That'd be 1, 6 as opposed to 1, 3. And you always try and do the lower numbers. Now, I'm not holding you to the alphabet rule. So if you put down 1-methyl, 3-ethyl cyclohexene, that would also be correct. Let's look at E, C, and D. And for C, ooh, double bond. What's the longest chain? 1, 2, 3, 4, 5. And don't forget, even though I'm showing bond angles here, this carbon is connected to this, to this, to this. So they're all part of the chain. Just like if you took a chain, you could wiggle it in different ways and still be connected. Now, how many carbons? 5. Pentane, double bond, change the ENE ending, ANE ending to ENE, pentene. Which carbon is of the double bond, either one, is closest to the end of the chain? This one, 1, 2. The other would be 1, 2, 3. So it's 2-pentene. Notice you have 2 of the same atom or group on one of each carbon, and it's below this plane of the double bond, and think of it below the 2 lines, and we call that cis. If they were opposite sides, the methyl and hydrogen were changed, that would be trans, but this is cis, so it's cis 2-pentene. Now, if we look at, get back. If we look at D, when you have 2 of the same group on one of the carbons of the double bond, in this case, even though it's part of the chain, we still think of it for cis and trans, 2 of the same group, CH3, you do not have cis-trans isomerism. Therefore, longest chain, 1, 2, 3, 4, 5, pentane becomes pentene, double bond. This is 1, this is 2, 2-pentene, we have a methyl group there, and that's how you do it. And let's move on to question 2. Question 2 is the other type of nomenclature question. Draw the condensed structure, draw the structure for the following IUPAC names of molecules. How do you do that? you start from the right end and move left. ENE ending, double bond. If it were ANE, no double bond, cyclohexane, 6-membered ring. This tells me a double bond. Now I put it between these two carbons, but for this problem, they could go through any of the two. Most of you did the first and second. That would be correct. All right, let's look at C. How do you know what to draw? You start the end. ENE ending tells you it's a double bond. If it were ANE, it would be octane, 8 carbons. Now notice the double bond starts at 3 and it's trans. So I do 1, 2, double bond. I show my bond angles here. My hydrogens are on opposite side. So this carbon goes down to 5, 6, 7, 8. Octane, 3 octane, trans 3 octane. Keep on going. Methyl, oh, you know what that is, CH3. Di means there are 2 of them, so I have 2 numbers. They're in carbon 5 and 6. All right. This is one of those times when Dr. White made a mistake. The correct name should have been 2-tert-butyl 3-isopropyl cyclopentene. I got my alphabet rules mixed up here. I made a mistake. Bad, Dr. White. Anyways, go from here, the right to left. ENE ending, double bond. That were ANE, be cyclopentane, 5-membered ring. So I'm going to say this is 1. You can start at any carbon, but most are going to do this. This is 1. This is 2. This is 3. Double bond is between 1 and 2. On a carbon 2, I have a tert or T-butyl group, and carbon 3, I have an isopropyl group. Oh no, the dreaded hydrogen virus attacked this file. This carbon here should have a hydrogen. Oh no. Now, you'll see when I have rings at the other school, because of a certain standardized test they gave as a final, I don't do that here. They use the line method on rings totally, and this is a way to grow isopropyl. This is a way to draw T-butyl. If I were talking to other PhD chemists, this is how I would do it too. But on the test for this course, I'm going to keep it simple. All right. Any questions on nomenclatures of alkenes? Well, in that case, let's move on. 3 types of questions. 2 nomenclature, give the IUPAC name of the following structure. The other thing you'll see on my test, draw the structure from the IUPAC name. And then the last thing, which later on in the semester we'll get more, we're already getting into it more and more, give the organic reaction products for the following reactions. And how do you do these? You look for what's different. What's not a carbon-carbon single bond or carbon-hydrogen bond should get your attention like that. Oh, it's broken. That's better. And therefore, if we look at A, I have this molecule reacting with hydrogen and nickel. What's different? Double bond. General reaction, double bond, hydrogen catalyst. I didn't put down, I should have. Catalyst can be platinum, palladium, or nickel. In this case, nickel. You break the pi bond. Remember, double bond is 1 pi bond, 1 sigma bond. You don't break sigma bonds except for combustion in my class. And you break the pi bond, each carbon gets a hydrogen. So if I do that, and I was in a hurry here, you could have the hydrogen sticking down here, you get butane. And same type of reaction in B, I like to give both. And here, double bond, hydrogen, platinum, same general reaction. You break the pi bond, Do you break carbon-carbon single bonds? No. So you have the 5 carbons in a ring, the methyl group, but I broke the pi bond on rings so you don't show hydrogen, and that's it. Now, I've already gotten a question from one of your colleagues, and that question is, what if I like to do more problems? And the answer is, make up your own. Once you have the general reaction, think of, oh, how many carbons do I want? Straight chain or ring? Oh, let's make a straight chain. I'm doing a double bond. Pick a number between 1 and 10. Oh, 5. And put a double bond there, react it with hydrogen. Maybe I'll throw a methyl group on there too. And then what do? After class or my office hours, you show it to me. You can hold it up to your camera if you want, or email it to me, whichever, and I'll tell you if you're doing it right. So if you ever need more problems you want to do, come up with your own. That's what I do when I'm in the class. Let me give you an example. Let's assume I want to practice that hydrogenation again. What do? I say, oh, I'm in the mood for 6 carbons, but they should be black. Oh, I'll put the double bond here. Do I want a methyl group? Sure. Put in my hydrogens, because don't forget, you know there are 4 bonds to carbon. I'll pick a catalyst. Let's do palladium, hydrogen. And why don't you try this one on your own? What would be the product or products for the following? I can't hear it ever on my end until I do the video. Is the clicking sound still there, or is it gone away? If it's gone away, go like this. Oh, good. I rewired some, or actually changed the paths of my cameras to my computer, so be away from something that might have given them interference. But I don't know if that's the source or not. All right, I think everybody's done. Let's do this. So how do you do this? You look for what's different. Oh, look, a double bond. I'm reacting it with hydrogen and a catalyst. And the catalyst can be platinum, palladium, which it is, or nickel. You break the pi bond. Each carbon gets a hydrogen. Do you break carbon-carbon single bonds? No. So you got 1, 2, 3, 4, 5 across plus a methyl here. So I'll do 1, 2, 3, 4, 5 across, methyl here. What are my 2 carbons with the double bond? Excuse me, these 2. Each one gets a hydrogen. And I know there are 4 bonds to carbon. Hopefully all saw my hand coming towards you. Now, one thing I mentioned before, on my test, Do you have to draw that? No. This is a general reaction that I'm teaching. You got to memorize it though. I don't do open book or open note tests in organic. Some of my best students always write this underneath. Some of my best students never write it. Whatever works for you. I'm writing it every time so you know the general reaction. In my mind, if I were doing this myself, this is firing up somewhere in the back here. And I see that as soon as I see the double bond, these conditions. But the point being, if you're practicing a general reaction, you want to do more, just make up your own molecules, put in the functional group, the reaction, do it, and then ask me. I can tell you within about 5 seconds, maybe 6, if you've done it right or not, probably less even. All right, let's continue on. If we look at C and D, let's do D. What am I reacting? What's different? Ooh, it's a big, scary, no, double bond. By the way, D is the organic chemistry instructor's trick on a test for organic chemistry. Big, scary molecule. Now, do you know what to look for? What's different? It's not. Double bond. I'm reacting now with halogen. We'll talk more about it in our lab later today. And you break the pi bond and each carbon gets a halogen. I don't have it here, but X can be fluorine, chlorine, bromine, or iodine. In this case, it's bromine. Do you break carbon-carbon single bonds? No. That's better. So I have 1, 2, 3, 4, 5, 6 across. 2, 4, 6 across. Methyl here, methyl here, methyl here, methyl here. Here are my 2 carbons with the double bond, which are these 2 carbons. I broke the pi bond. Each one, in this case, gets a bromine. Now, if we look at E, what's different? Double bond reacting with HBr, which is HX. X in this case can be chlorine, bromine, or iodine. Double bond, break the pi bond. One carbon gets H, the other gets X. It follows Markov-Nikov's rule. The rich get richer, the poor get poorer. Nah, yeah, actually, that's how I learned it. The carbon with the most hydrogens on the double bond gets the hydrogen. The other carbon gets the halogen. So now you got to use your high levels math skills. Which is higher, larger, 2 or 1? Time's up, hopefully I'll pick 2. So yeah, 3 carbons, 3 carbons. This carbon here gets the hydrogen when you break the pi bond. This carbon here gets the bromine, which is X. Now, in F, the same thing, except now we've got a ring. Dr. White and Mother Nature love rings. I really do, and she does too. Students hate them. This is one of the reasons. All right, I see a double bond. I'm adding HX. Remember, X can be chlorine, bromine, or iodine. In this case, it's iodine. H goes to the carbon double bond that has the most hydrogens, and the X, in this case, iodine, goes to the, oh, wait, there's no hydrogens. You don't show that on a ring. So now what you have to do is count bonds. This carbon here has 1, 2, 3. 4 minus 3 is 1. This carbon here has 1, 2, 3, 4. 4 minus 4 is 0. Bottom one, 0, 1, which is the greater number. Hopefully you pick 1. So the hydrogen will go here and the halogen will go here. And you don't show that on it. You lose the double bond. Iodine goes to this carbon. The methyl group and isopropyl are still on the ring, and the hydrogen goes there. Now, if we look at G, double bond again, look for what's different. Acid, H plus is how we say acid in general and organic, and water. Double bond, acid, water. Think of water as H and OH. You break the pi bond. One carbon gets the hydrogen, the other gets the hydrox group OH, and it follows Markovnikov's rule. The carbon with the most hydrogen gets the hydrogen, in this case from water, and the other group carbon gets the hydroxyl group. So if we look here, we have 3 carbons. We're going to end up with 3 carbons. You break the pi bond. Now we look here. This carbon double bond has 2 hydrogens. This one has 1, which is the greater number. And times up, hopefully you pick 2. Hydrogen goes here, hydroxyl group goes there, and that's what you get. And here we have a ring. And this carbon here has 1 hydrogen, this has none. One carbon gets the H, the other gets the OH. You break the pi bond, everything else still comes along for a ride. Hydrox group here, methyl here on this carbon. Now, if you put the methyl here and the hydrox group here, in other words, switch them, that would be okay. Any questions on reactions of alkenes, carbon-carbon double bonds? Oh, I got some questions before we move on. Did anybody happen to think of gas alkanes when you went by a gas station? Did anybody happen to think of alkanes if you turned on your gas stove? Did anybody happen to think of alkanes if you use Vaseline or baby oil? Why me? All right, Dr. White will not give up. When you leave my class, organic chemistry is all around you. Again, I stole that from SpongeBob. And it won't hurt for you to think about it. Trust me. By the way, with alkenes, did anybody look at a tomato or a carrot and think, wow, it has that color because of double bonds? Don't you want Dr. White to smile? Think about it. It won't hurt. Next time you see a tomato or a carrot, think about that's double bonds causing that color. Dr. White will not give up. I've got a lot of weeks to work on you to make you think about organic chemistry. All right, any questions on alkenes? Let's move on to triple bonds. Now, triple bond, 3 lines, and here I ask, and it's important to read questions, give the IUPAC name for the following. Common name, which I expect you to know so you can draw the structure of this as acetylene, but the IUPAC name is ethyne. Remember, for a triple bond, name the longest chain. You're not going to see a triple bond and ring in my class, or I've never seen one in my life, except maybe once decades ago in an obscure paper. But triple bond, you name it as an alkane, longest chain, drop the A on the ending, put Y on E. You need a number, except for A is the only exception. And there's no sister trans because this is linear. Now, why isn't this 1 ethyne? Because you can't have 2 ethyne. Whichever carbon you want to call it is the end, and therefore that's the molecule. Now, one thing I do want to mention, the software I use to draw structures, like for your test, can either left justify something. This is right justified. Meaning this is on the right side of this carbon, or left justified. And this is only for the end carbon on this side, your left. And these are both the same and both correct ways of writing it. And I just wanted you to notice that because either way is correct. Oh, let's do D because I think I might have caught some people. Dr. White can be tricky. How many of you put down in the name for D, T-butyl? I catch anybody? Because it looks like a T-butyl group, but no, you find the longest chain. What's different? Triple bond. What's the longest chain? 1, 2, 3, 4, 5, 6. Let's do it again. 1, 2, 3, 4, 5, 6. Hexane, triple bond. Drop the A and E, put Y and E. Hexine, starting from this end or this end, is 3 hexine. But I'm going to start from this end. This gives us the 2 methyl groups, the lowest number. 2 of them dimethyl. They're on the same carbon. I still need 2 numbers. 2, 2 dimethyl, 3 hexine. Now, the other type is give, and here I have IUPAC, and I should have taken that out, because on my test, if I ask you to learn a common name, and we'll be getting to more on test 2 material, more functional groups, I'll teach you common names, because they're in your daily life. I will never ask you, say for A, what's the name, common name of this, but I will ask you to know how to draw it, because you're likely to see the common names like this on labels of things you buy. So here, acetylene, simplest molecule with a triple bond. I have it written this way. If we look at C, we start here. Y and E ending tells you triple bond. That were A and E, heptane 7, 1, 2, 3, 4, 5, 6, 7. Then on carbons 2 and 5 are methyl groups, dimethyl. So 1, 2. Then the triple bond between 3 and 4, and then the last carbon on 5. 2, 4, 6, 7 heptines, 7 carbons. All right, let's look at the reactions of triple bonds. And if we look at the first 2, well, let's do B. What's different? What's not a carbon-carbon single bond or a carbon-hydrogen? Oh, look, a triple bond. And what are we reacting with? Hydrogen, the catalyst I forgot to do on the original word practice problems. I apologize. My printer died a while ago and I haven't replaced it, or I would be fixing these. Triple bond, hydrogen. Now, remember, triple bond has 2 bi-bonds, 1 sigma bond. Therefore, you need more than 1 mole or molecule of hydrogen. And organic chemists are lazy. So instead of balancing this, we just put the letters in the bracket, bracket, excess, close bracket. That means you have excess hydrogen. You have all the hydrogen in the world that anything hydrogen can react with will. In this case, triple bond break both of the pi bonds. Each carbon gets 2 hydrogens, and that's what happens. So you have 1, 2, 3, 4, 5, 6 across, 2, 4, 6 across, 2 methyls here. They're still there. Each carbon of the triple bond gets not 1, but 2 hydrogens, and there you go. Now, halogenation is where you react bromine, chlorine, fluorine, or iodine with a triple bond. Again, because you have 2 pi bonds, you need 2 moles or molecules of halogen. Organic chemists, we're too lazy. We'll just put the letters excess in brackets, meaning you have all the bromine in the world that will react with anything bromine will react with. Here, triple bond, each carbon gets gets a halogen. No, they get two because they're 2 pi bonds. And here, 3 carbons, you don't break carbon-carbon single bonds. 3 carbons, I broke to 2 pi bonds, and each carbon of the triple bond gets 2 bromines. And the same thing down here. We have a triple bond, 1, 2, 3, 4, 5, 6 across, 2, 4, 6, 2 methyls, 2 methyls, and then I break the 2 pi bonds, and because of that, each carbon of the triple bond gets not 1, but 2 chlorines. Now, there are other reactions of double and triple bonds that I know, but I'm not going to teach you because I'm teaching you the main ones because I want to spend time on stuff I think you would find more exciting, and that is later on in the semester when we go out in the real world. By the way, coming attraction. You won't believe what Dr. White can get into in this class. I mean, you won't even, he's really doing that? And the answer is yes. All right, any questions on double bonds or triple bond, nomenclature, or chemistry? One thing I'll mention, and I'll mention it next week about test number 1, same thing is true at 2, test 3, 4, and the final. That is every question that's on the test, I'll have talked about the concept behind that question, how to do it and answer it at least twice in lecture. Usually it's a lot more, but at least twice. And that's my promise to you. Every question that you're asked to answer, the only thing I don't go through is, I guess it's sort of a question, your name. All right, let's continue. We're talking about alcohols. And remember, alcohols, carbon with a hydroxyl group. OH, hydroxyl group, R means anything with carbons. As long as you have a molecule with a carbon with a hydroxyl group, we call that an alcohol. And you find the longest chain of ring that has the hydroxyl group carbon in it, name it as an alkane or cycloalkane, drop the A on the ending, or the E you can think of and replace it with OL. Or the A and E replace with A and OL. I like this is what the author of the book you're using had, but I like drop the E at OL. Next, you need a number where is that hydroxyl group on, and finally the rest of the IUPAC are the same. And I think we did some examples. Let's do 1 or 2 more. And what would be the IUPAC name of the following molecule? Your turn. And don't forget, when you're done, give me a thumbs up, or you can smile if you got your video on. Thank you, Paige. Remember, name the longest chain is an alkane. Drop the E, add OL. You need a number which carbon has the hydroxyl group. Then name the alkyl groups the way you always have. The carbon with the hydroxyl group, you have two choices, should always have the lower number. All right, let's do it. All right, look for what's different. Alcohol. How many carbons in the longest chain? 1, 2, 3, 4, 5, 6. Or you could have counted to check 1, 2, 3, 4, 5. And therefore, I'm going to say 6 is greater than 5. The longest chain is 6. That's hexane. Drop the E, add OL, hexanol. 1, 2, 3. If I started the other way, 1, 2, 3, 4. 3 is less than 4, so it's 3 hexanol. And then I have my 2 methyl groups on carbon 2 and 4. 2 methyl groups are dimethyl. And which carbons are they on? 2 and 4. So it's 2,4-dimethyl, 3 cycle. I want to do a ring in my brain. I like rings. 3 hexanol. And that's how you do it. Now, the other type of skill always is, one, give the IUPAC name. The other is draw the structure. And I don't remember. Everybody, give me either thumbs up or thumbs down, or just thumbs up if it's yes. Did we go from names to structure with alcohols yet? I don't think we did. Okay, my memory still works. I hope. All right, I'll do this one and I'll give you one. How do you decode this to know what the structure is? You start at the end, move from the right to left. OL ending. It's an alcohol. If this were an E, cyclohexane. Therefore, I'll draw a 6-membered ring. And then carbon 1, you can put it on any carbon, but most are going to do it here, has a hydroxyl group. This is 1, then either here or here, and most are going to go counterclockwise, is 2. And I have an isopropyl group. And I now have 2 isopropyl cyclohexanol. Your turn. Why don't you try this one? Draw the structure for 2-tert or T-butyl. I'm going to be a lazy organic chemist now. John lost your rookie status. T-butyl cyclopentanol. Thank you, Samantha. It's interesting, the class I'm just finishing up now about online teaching, which is asymmetrical. So people are communicating through a discussion board. One of the faculty members, or all faculty, complained about how on her online course, when she's giving a Zoom meeting, not everybody turns on their video. And I wrote back, well, what if they don't have a webcam or it's not working today? Why should you get upset? They're showing up. That's what counts. All right, time for Dr. White to get to work. How do you draw this? How do you decode this? You start from the right, move left. OL ending. What does that mean? Alcohol. And if this were an E, cyclopentane, 5-membered ring. One carbon has the hydroxyl group, and you go clockwise or counterclockwise. This is carbon 2. If this is 1, which it will be, that's why we don't have a number, because it always will be when it's the only functional group, and a T-butyl group, which Dr. White loves. He also loves isopropyl. And you know there's 4 bonds to carbon, so I know how many hydrogens, and that's how you do it. Haven't done it today, so I better do it. How many bonds to carbon? 4 bonds to carbon. 4 bonds to carbon. This hand's working better today. 4 bonds to carbon. Remember that. It's going to be your friend on test number 1. And if I look at my watch down here, I'm going to give you an extra 30 seconds. Come back at 1:55. We'll go a little more into alcohols, and then we'll have our lab. You're going to get out early today like you would on any Wednesday. And with that, I'll see you in 5. I'm coming back. I shouldn't have done that. Somebody might think I'm leaving. I'll be back in 5. And so should you. I haven't done it all afternoon, so it's time to call you all back to class. Come on back. Oh, it worked. Some just personal advice from Dr. White. Never, ever let go of the little kid inside of you. I haven't. Always enjoy life and don't let go of that little kid. I never have. I still enjoy seeing fire engines as long as they're not coming to my house because I like the blinking lights. But anyways, let's get back to work. All right, today I'll go a little longer. Normally on a Wednesday, after the first 50 minutes, take our break, and then I'll do the lab. If we were at ECC, we would do the same thing. And then you go and do this with the chemicals, but unfortunately, you're not doing this part, but I'm giving you the information so you can do this part when you write it. So you're getting the same thought process and experience. And since none of you are going to be chemists, well, we can get by where you're not actually mixing the chemicals. All right, now, one name I didn't talk about, and I better talk about now, and that is when you have a benzene ring with a hydroxyl group, and you say, oh, you call that benzyl? No. For many eons, this was called, and I pronounced it a certain way, and I worked at a company where we bought, about 150, 200,000 pounds a week of this compound. It's spelled this way. Wait a second. I better put on my writing hat. Let's try that again. I pronounce it phenol. People mispronounce it phenol. And at one company, Borden Chemical, I had a running argument with other PhD chemists, and they'd say it's phenol. I said, no, it's phenol. But since we're not doing enunciation, you don't have to. This is both the IUPAC and the common name, because it was the common name before it became the IUPAC. Now, just like toluene, this is considered a substituent. So if I go to my whiteboard where I have more room, question is, what's the IUPAC name for this? Well, oh, benzene ring, that's different. Hydroxyl group on a benzene ring, that's phenol. Ooh, alkyl group, 1, 2, 3 carbons to the N carbon, and propyl. This is 1, 3 disubstituted, and therefore we call that meta. And that would be meta and propyl phenol. Oh, let me give you one to try. There you go. What would be the IUPAC name for that? Remember, 1, 2 is ortho, 1, 3 meta, 1, 4 para. I'll say that slowly. Remember 1, 2 ortho, 1, 3 meta, and 1, 4 para. Oh, it's Dr. White being obnoxious Wednesday. And when you're done, give me a thumbs up if you like. All right, I think everybody's done. Let's do it. What do we see that's different? Oh, look, a benzene ring, and it has a hydroxyl group. Immediately, that's phenol. And what do I have? I have this on there. What is that? You can either put tert, or now Dr. White's going to be, and you can be too. Most organic chemists would call it a T-butyl. And notice it's 1, 2, 3, 4. 1, 4 disubstituted is para. And that's what it is. Now, I'm going to give you the other type of nomenclature question, which we did with alcohols. Well, why don't you do this? Draw the structure of phenol. I think everybody's done, so let's do that. Phenol, OL ending, and actually the whole name you have to learn, means a benzene ring with a hydroxyl group. If you just wrote this, you'd get no points, because this is cyclohexane. Don't forget to put the circle or the bonds whenever you're talking about a benzene ring. Now, before we move on to alcohols, I forgot to do something in double bonds, and this you do not have to write down. Does everybody know what that is? It's transparent. Opposite, transparent. You can all go boo. Just wait, I got more good ones down the semester. I hope I don't scare you away. All right, let's move on. Now, in the coming chapters, we're going to talk about more functional groups like this one that have been around for eons. Alcohols have been known since, I think, the Roman or Egyptian times, and I'm not sure when the name alcohol was originally applied to it, but they're common names. And common names, you'll find on an ingredients list. I think that's something you should know. Now, listen carefully. On a test, I'll never ask you, here's the structure, what's the common name? I'll never ask you, here's the structure, what's the common name? What I will do is I'll give you the common name and ask you to draw the structure. So let's look at alcohols. There are a couple of alcohols that always use the common names for more than IUPAC. And these are key alcohols. Now, how do you do common names? Is derived by naming the chain the hydroxyl group is on as an alkyl group, and then adding at the end the name alcohol. C-board for ethyl alcohol, isopropyl, and tert-butyl. Uh-oh, I better get to work. Anybody writing this down? I'll give you a second or two. I'll never ask you on a test, what's the common name for how do you get the common names? But I will expect you to know how to do that. So let's get to work. And if you were in a classroom, you'd see me writing this on the board, and you just have to be patient and wait. All right, let's look at the first one. We have 2 carbons, and this would be, as we mentioned the other day, ethanol, which is found in good stuff like vodka, also Dr. Whitelove's Canadian Club. But anyways, now this one, oh, what's the longest chain? 1, 2, 3, propane, alcohol, propanol. And notice that this is 1, this is 2, that would be 2-propanol. Now, if we look at this last column, which I can write 2 different ways, you look at the top one, alcohol, the longest chain is 3 carbons, so that's propanol. And this is 1, this is 2, it's 2-propanol. And notice what's left over is a methyl group on carbon 2. So this is 2-methyl. There's an L there, I ran out of room, hold on. If this ever happens to you on a test, you can split it because I'm running out of room. Now, Dr. Whitefield's, this would all be normally 1 line, 2-methyl, 2-propanol. Now, unfortunately, what I can't do on the screen is put my hand over the whiteboard, but I can circle it. You look at this right here, not the oxygen, this right here, that's an ethyl group. Therefore, the common name for this molecule is ethyl alcohol. And if you look on bottles of wine, you'll see the ethyl alcohol content. Now, if we look at this one, what alkyl group would that be if you ignore the hydroxyl group? 3 carbons, center carbon, isopropyl. Nobody ever calls this 2-propanol. Everybody calls it isopropyl alcohol. Now, interesting thing, if you take about 70%, and I'm going to use an abbreviation IPA because I'm worked in industry, isopropyl alcohol, and 30% water, mix it together, you get a homogeneous solution, which people sell and people buy, called rubbing alcohol. And that's the name of the product that has this mixture. Now, why do they call it rubbing alcohol? I don't really know, other than maybe you rub it on your skin because it's a disinfectant. Now, about 8 or 9 years ago, you started to be able to buy, maybe a couple more years, at places like Walmart. They now sell 90% rubbing alcohol, 90% isopropyl alcohol, and 10% water. And I have a bottle in my house, long before COVID-19, and luckily I do because I use that to disinfect things like my ring when I come back from the grocery store. Yes, I'm super careful. It kills that stuff, but you just got to let it dry under. You can't wipe it off after you wipe. Take a Kleenex, put some rubbing alcohol, and just go like this and let it dry. And it works pretty good. And now if you go to Walmart or other places, usually those shelves are bare because I'm not the only one who knows that. Now, Do I have time? Oh, I do. A rubbing alcohol, solution of isopropyl alcohol and water, 70% or higher, kills germs. I'm not talking about I guess viruses too. And when I was a kid, and even till older, now if you go to a doctor's office and they take your temperature, they have the electronic type. They either stick it in your ear or, I haven't seen it in a long time, put it under your tongue. Well, back when I was a kid in high school and even college and later on, you go to a doctor's office, they had the glass mercury thermometer. They'd stick it out under your tongue and you had to wait 3 minutes. And it tasted awful. Why? Because they had a special container filled with rubbing alcohol, and between each patient's, they'd first wipe it off with some cotton with rubbing alcohol and stick it in there. So when they stuck it in your mouth, there was still some of that on there. Ugh, it tasted awful. Now, let's look at the last one. Now, I have it drawn this way, but if you rotate it 90 degrees, you now have this. And why did I do that? Because it's easier to see what's this alkyl group here, and that's the T-butyl group. And a T-butyl group with a hydroxyl group on it, the common name would be tert-butyl, but nobody calls it that, T-butyl alcohol. And these are the most common names. And I would ask you to learn these three. So on a test, if I write, and this is the only way I would do it, draw the structure of isopropyl alcohol, you should know that's this, ethyl alcohol, T-butyl alcohol. And I did phenol already. All right, next two slides, I'm going to turn off the switch. Click. Will this be on test? No, but it's good background knowledge. You should know. That'll help explain other things I'll talk about. Now, alcohols can hydrogen bond. And if you remember, water looks like this, and it has a dipole moment because of the difference in electronegativities of oxygen and hydrogen. There's a slight, and this means slight, little delta means slight, positive charge here, very slight negative charge in the oxygen, same thing on this hydrogen, positive. If I take another water molecule, same thing. And as you've learned in life, opposites attract. When you have opposite charges here, there's a very slight attraction, and we call this hydrogen bonding. I don't have to do that, we just call it this. And hydrogen bonding is the reason water at room temperature is a liquid, not a gas. It should be a liquid, but because of this very important but tiny force, well, it turns out alcohols. Now, in hydrogen bonding, it's a weak intermolecular molecules enter. If you go to international flight, you're going outside the country. Intermolecular means outside a molecule, between two molecules, attraction between the non-bonding electrons, that's what's on the oxygen, and the hydrogen. And it's weaker than a chemical bond, but plays key role in solubility and boiling points. And water, alcohols like water, has a higher boiling point than corresponding molecules with the same chemical molecular weight. Now, let's look at alcohols. I'm just drawing it this way. And I'll throw in a water molecule too. And here between alcohols, you can have hydrogen bonding, which is important why alcohols have a higher boiling points than, say, alkanes, which can hydrogen bond with the same molecular weight. And it can hydrogen bond to water. And that explains why alcohols are soluble, the smaller ones. When ours gets larger, like 8, 10, 12 more carbons, then it's no longer soluble in water. But if it's too like ethanol, it is. Oh, by the way, do not try and convince bartenders when you go into a bar, oh, do you know why you can make mixed drinks with alcohol in it? It's because of hydrogen bonding. Trust me, they do not want to learn about hydrogen bonding. So don't do it. Dr. White found out the hard way not to do that to a bartender. That was in my younger days when I was really gung-ho in chemistry. Oh, I'm still gung-ho in chemistry. Now, switch is still off. Alcohols are very weak acids. Acid is something that donates a proton. And the equilibrium, the little arrow tells you it's very weak. If it loses a proton, this is this, and this happens less than water. This is a very weak acid. This is called alkoxide, a very strong base. And alcohols are very, very weak acid, switches off. But turns out phenol is a stronger acid than most alcohols. Why? Because this anion, called the phenoxide anion, which I won't ask on a test, see board, well, you can see on top here, I can draw another resonance form, and this won't be on the test. I can draw more than one, and the more resonance forms, oh, plus H plus, and this is this type of equilibrium. The more, and I could draw two more, the more resonance forms, the more stable, the more likely it'll go to this side, and therefore the more acidic. And turns out phenoxide anion, I'm an expert in. My last patent, I was able to do stuff with phenoxide anions, nobody else could. And so I know this stuff a lot. Now, switch is still off. Alcohols can be bases. And what's a base? Something that accepts a proton. So if I add an acid in chemistry, organic chemistry, H plus is an acid, acid-base reaction, and what you form is this cation. Now, in the classroom, I'd use my hands, but I can't do on a whiteboard, but I can use the red pen. Anybody see something familiar? Two hydrogens and oxygen. Two hydrogens and oxygen. I wonder what that could be. Two hydrogens. It's water. And whenever you can lose something stable from a molecule, it says, hey, I'm out of here. You lose water. That's what this means right here, minus. And what we call, I'll teach you later on, This is called the carbonium ion. In the last 15 years, they call it the carbocation. I don't like that. I like the old name. It sounds cooler. Carbonium ion. And it's the first step in a couple of very important reactions of alcohols. All right, switch is back on. Hold on, I better show you. Click, it's back on. Could this be on a test? Now, oh, you already know this reaction. Now, fancy word time warning, synthesis. I'm a synthetic organic chemist. What does synthesis mean? To make. And this is one way of making alcohols. If you take a double bond, react it with acid and water, you make an alcohol. Now you know what this is. You already seen this reaction. And this is the only reaction I can put on two tests, 1 and 2. By the way, my test 1, 2, and 3, I don't mix old reactions from test 1 and test 2. That's not fair. So let's take a look at this reaction. All right, since you can't see it, because I took off the slide, one of the things I always keep on forgetting, writing too close to the top. And it's time for you to have some fun. What would be the product or products of the following reaction? And when you're done, give me a thumbs up, especially those of you who don't have your video on when you're done. Or if you want to turn on your microphone, you can always say, I'm done. All right, I think everybody's done, or their thumbs aren't working. Ah, somebody's thumb is working. All right, let's do it. All right, what's the 3 points each? what's the organic product or product for the following reaction? Well, first you look, what's different? Double bond. What am I reacting with? Hydrogen, acid, H+, and water. What's the general reaction? Well, it's up here. I was nice enough. Double bond, acid and water. Remember, water is H and OH. You break the pi bond. Remember, this is one pi bond and one sigma. And one carbon gets the H, the other gets the hydroxyl group. Follows Markovnikov's rule. The carbon width of the double bond that has the most hydrogen gets this hydrogen. The other carbon double bond gets the hydroxyl. So here are my two carbons of the double bond. We got to do some high-level counting. How many hydrogens on this carbon? 2. How many on this one? 0. Which is the larger number? Time's up. Hopefully all pick 2. Do you break carbon-carbon single bonds? I got to do this. No, you don't. All right, everybody catch that? No, you don't. That's good advice. So I have 4 carbons across. 1, 2, 3, 4. On this carbon, I have a methyl group. These are the 2 carbons of my double bond. Hydrogen goes to the first carbon. Second carbon gets the hydroxyl group. And now I know there are 4 bonds to carbon. Oh, I got to do this. There are 4 bonds to carbon. Does this look like it's coming right at you? 4 bonds to carbon. That's always going to be your friend. And I'm going to put the remainder carbon hydrogens in. I find when I'm doing these reactions, leave the hydrogens to the very end. Makes your life easier. And that's the product you get. All right, as I look at the clock, it's time for lab. Lab time. And if we are going to lab, I'd say, everybody, put your goggles on, but we're not. We'll be doing mental exercises. All right, if you look in the assignment area of D2L, you'll see Alkenes, I think I call it lab, and there's 2 to download. I'm gonna have to, I made a mistake. I put the wrong URL for one of those. You'll see in a second. All right, let's assume we're in the lab now, and this is exactly what I would do. I'd be standing up in front of you, not sitting in front of a computer, and let's do the lab. And today's lab, let me just check with everybody. Everybody see Alkanes and Alkenes lab? Give me a thumbs up if you can see it. Thank you. All right. And this is what I'd be handing out to you Monday before the lab. So you had, like I said, because of that course, I've been running late on things. Next week, I'll get this up on Monday before the lab. And remember, all hydrocarbons are very flammable. Don't light any matches during the lab, ever. And as I would tell you, use proper waste bottles, which I would teach you. All right, now, as I mentioned last time, but I'll mention again, years ago when I took over this course, the labs they used were pitifully bad. I'm being very polite. They stunk. And I challenged myself, you're an organic chemist, write new labs. And I did. And part of my philosophy in writing new labs was, unfortunately, we're not in the lab right now, but if we were, give you exposure handling certain organic molecules, understanding some basic principles, and teaching you some important things about them. Let me remind you, anything we do in the lab will never be on the test or any test unless I talk about in the lecture. We're not in lecture now, we're in lab mode. See? So remember that. Now, the first thing that's interesting about the alkanes is what do they smell like? And if we were in the lab, you would be smelling different alkanes and alkenes, double bonds. And what I've done for you is what students over the years have told me. I've written down what it smells like. Now, let's talk about limonene, and I'm going to help you out. The structure of that. Let me check if there's another double bond in there because I don't use this that often or think about it. Yep, there was another double bond. Nope, wrong place. And ENE ending, this is a common name. This is not the IUPAC name. Notice there are two double bonds here. And if you were to smell this, you'd smell a lemony smell or fruity or lemony fruit like that or citrusy smell. Now, how many of you have ever bought a cleaning product and you smell it and say, oh, lemony good, I'm going to buy this, or I like using it? No, they don't squeeze any lemons. Synthetically, they make limonene and they put it in there. And you've been conditioned by Madison Avenue that when you smell that lemony fresh, ooh, this must be good cleaner. And a lot of them are. I'm not saying they're not, but you've been conditioned to like that odor. And they put it in there just for that. But anyways, let's get back to the lab. Now, for this lab, this part, you'd smell these, and this is what most students smell like. Naphthalene, as I mentioned the other day, is the molecule used to make mothballs, and it's got a pretty strong smell. All right, that's the first part. Let's move on to the next part. In organic chemistry, before the advent of the electronic equipment we now have, spectroscopic means to identify molecules or functional groups of molecules. Organic chemists, say in the late 1800s through the early 1940s, used physical or tests that had color change. And this is one of them. Identification of alkenes, a double bond by halogen addition. And pay attention because you'll need this knowledge when we talk about or you answer the questions, which you will be able to. If I have any molecule with a double bond and react it with halogen gas, especially Br2, you break the 2 pi bond and each carbon has a halogen. You can write it this way, or I could have written it this way. R prime, which I haven't used yet, is like X and Y. That means R on this side, how many carbons and hydrogens can be the same as R prime, or it can be different. Anytime you see a molecule that has a double bond and add a halogen, this will happen, as you learned in the classroom. Now, if we use bromine, this is a red-brown color. And when you add it to an alkene, this reaction happens immediately. And most organic compounds are either slightly, very slightly yellow or clear. And what the test is, you take a sample and you add some bromine solution. And if it stays clear, there's a double bond. If it doesn't stay clear, it goes red-brown because you're adding this. That means you have an alkane. And now, through the miracle of the internet, everybody see the alkane test tubes? Thank you. Let's watch. See, they're adding the bromine solution, which is a dark brown, reddish brown, and see how the solution is becoming reddish brown. That's because the bromine is still in there. It's not reacting. Alkanes have no double bonds and won't react with it. Now, the other side has a double bond. Look how quick that's reacting. And that's why it stays clear. So if you have a clear solution, you have an alkene. If you have a reddish brown, you have an alkane. And in this one, I do the demonstration because years ago at the other school, we did the same experiment and I sort of know how it happened. One student got bromine solution on the back of the neck of another one. And it's quite a hazardous solution. I have to wash it off with a got it off, then sent them at that time. We had a nurse in the school. They got rid of her to save money, which was stupid, but that's another story. And after that, I said, another lab, it happened again on the neck, but elsewhere. I said, this is too dangerous. I'll do it as a demo like you saw in the video. And what you'll do if you were watching me is take notes, and I'd put hexane, put the bromine solution in, you say, oh, it turns red-brown. I'd have one hexane and it'd go clear. Now, if you notice, I don't have a number here because it matters what we had in the stockroom Dr. Daly would put out. Well, let's assume this is one octane, and that would stay clear. Limonene, which has two double bonds, stays clear. Now, to make this lab interesting, you would also test two compounds in the bottles that are unknowns. One, I got very fancy names, unknown A and unknown B. And if you put when you put the bromine, or watch me put the bromine into unknown A, it stays clear. When I put it into unknown B, it goes red-brown. And that's that part. Now, next part, another way of identifying double bonds is by oxidation with potassium permanganate, KMnO4. This is purple in solution. I didn't teach you this reaction, but whenever you have any double bond, react it with a solution of potassium permanganate, you break the pi bond, and each carbon of the hydroxyl group gets double bond gets a hydroxyl group. But this is called an oxidation reduction, and usually this is called oxidation, but it's actually oxidation. If this gets oxidized, this gets reduced. What does it get reduced to? Manganese dioxide, which has a brown color, but in solution, I like to call it muddy brown. If you've ever been to parts of the United States with reddish clay dirt and you make it wet, that's muddy brown. Now, sometimes other things are formed which would have a greenish color, but that usually doesn't happen. So if you add potassium permanganate solution and there's a double bond, it goes from purple to muddy brown. And in this part, you do your own. Once in a while, for certain people, potassium permanganate can stain skin. It definitely stains clothing, so be careful. But we always wear gloves for this. We have them in the lab, and I have to, on the YouTube, for some reason, I cut and paste the wrong one. Let's take a look at this one. And you should see a red test tube on your screen. Do you see it all? The red test, yes, you do. What? You don't? All right. Zoom tells me you should be seeing it. Let's try it again. Do you see it now? Thank you. I really appreciate you, my thumbs up people. All right, let's turn this on. Notice potassium permanganate is a purple color. You would do it the opposite, add this to the, now they're adding, or should be adding, notice they're adding the alkene. See how it's becoming brown? And if you wait long enough and you add enough, it becomes a muddy brown. And that tells you, stop, this muddy brown, that's how it actually in the lab when we do it, it's much darker and looks like mud and brown, muddy brown. I'll fix the links and re-up later today, the lab, so you get it. Now, what would you do in the lab? You try cyclohexane, it's purple. 1-hexene, it would be muddy brown. This would also be 1-octene. Well, once in a while we have 2-octene. It'll be muddy brown, limonene, muddy brown, and now once again, unknown A and B. Unknown A is muddy brown, unknown B stays purple. And for the lab, what you have to do is answer the questions. Now, the first one, I'm asking you to draw the structures of cyclohexane, 1-hexene, octane, 1-octene, limonene, and naphthalene. Just draw them here. And then I have the other questions, such as in 3, please explain using a chemical equation and words how a solution of colored bromine, Br2, when added to an alkene, does not cause the color of the alkene to change. And finally, the big one, number 4, please identify A, unknown A and B, as either alkane or alkene. You don't have to name a structure. This is A an alkane or an alkene, is B an alkane or an alkene. And now the hard part, not really. Describe what data in your experimental results from part 2 and 3 allow you to make that identification. And that's what you'll be uploading. And this lab that I just discussed right here is due next Wednesday. By the end of the day, hopefully you got the lab melting points you've uploaded. If you have any trouble doing that or understanding it, don't forget, tonight, my office hours, if we had been at ECC, I would have ended we would have started earlier and you do the lab. And by now, this is a quick one. Within 10, 15 minutes, you'd be out early. So guess what? I'm going to let you out early. With that, I'm done. If you have any questions, I'll stick around. I get to use this again. Bye. Be healthy again, gesund. Don't forget, on Monday, I'll be going through the aromatic problem set. Plus, I'll be doing the world famous review for test number 1, which will be a week from today. And over the next couple of days, I'll put up and put out announcements, send out an email describing test number 1. And we'll talk more about it on Monday. With that, I'll see you on Monday. Gang gesund, be healthy.